So the best way to learn about something is to take it apart and put it back together and see if you can do it. And in this video, we're going to do that with Stable Diffusion 1.5. We're going to take it apart in its component pieces and try to run it and see if we get a good result. This is the simplest Stable Diffusion 1.5 explanation video. We'll be simplifying it to its most basic pieces in order to try to understand how the pipeline works. So the first thing that you'd want to do to get started is, well, first of all, in Google Colab, pip install transformers and diffusers to get started. Now, Hugging Face provides a very handy pipeline object with which you don't really need to know how Stable Diffusion works in order to run it nonetheless. And we're going to run that first of all, and then we're going to take the pipeline apart into its component pieces. So first of all, you import from diffusers the Stable Diffusion pipeline. We're also going to need torch. The model we're going to be using here is the Runway ML Stable Diffusion model. And then we're going to create the pipeline, call it pipe, Stable Diffusion pipeline from pre-trained model. And we're going to cast it in float 16 to be able to run it. And we're going to send it off to CUDA. Now this is going to take just a bit of time because Hugging Face is actually going to download the model from the hub if it's not already done and cached. As the download is proceeding, we can actually, just to try it out, run a sample or type out a sample prompt. So the prompt will be anything that you want. Photo of a cat is fine, as suggested by the IntelliSense here. Photo of a cat. And all you have to do afterwards is to run the pipeline on the prompt and get an image. In this case, we're not necessarily going to save the image, but simply display it. And there you have it. It's a picture of a cat. Works pretty well. And now what we're going to try to do is to reproduce a picture of a cat, but without using this pipeline object, and simply hard coding all the steps ourselves in order to learn how Stable Diffusion actually works behind the scenes. So any diffusion system, well, has 4 main component pieces, and we're going to isolate them. So first of all is the unit. This is pretty much the working horse, the main driver, the model that actually does that computes the image. We have the VAE, which is stored as pipe.vae, and we're separating these pieces so in order to be able to use them without the pipeline object. Then we have the scheduler, which is pipe.scheduler, and finally we have the tokenizer as well as the embedding model. We're just gonna, for this, I'm gonna regroup them into the same aspect because the idea is to convert the prompt into an embedding that'll go into the unit, which is the main model that'll generate the image. So we can just start here, tokenizer, which is the tokenizer, and then the clip embedding model, which I think is pipe.clip. So it's not pipe.clip. We can inspect our pipeline object to see where it is. And it's the text, it's called text encoder, which is a clip text model. So text encoder. Perfect. So now we have all the separate pieces together. And what basically a diffusion system does is it progressively denoises random noise in order to generate an image. So your unit is going to receive a point in time The earlier it is, the more noisy the image. The later it is, the less noisy it is. And for each time step, it takes in the noisy image and outputs predicted noise. That is what it thinks is the noise, and then the scheduler's job is to take that predicted noise and to subtract it from the noisy image to get a slightly less noisy image. And the loop has to be run over every time step with the unit and the scheduler working together. And at the end, what it's going to output is not an image, but basically a latent representation of an image. And the reason that's done is the latent representation actually has more dense image representation. So it's going to be a 64 by 64 tensor, whereas an image that you want is 512 by 512. And the VAE's job is to take that latent representation and to convert it into a full-fledged 512 by 512 pixel image. And that's pretty much it. And throughout this, at the beginning, we will use the tokenizer and the clip model to convert our prompt, which is a bunch of words, into an embedding that the model can understand. So let's get started. First of all, we have our prompt, which is a photo of a cat. And what we will be doing is we will be tokenizing it. So tokens are tokenizer prompt, and we're going to be getting the PyTorch tensors and also sending it to the GPU. Perfect. And after that, once that's done, we will not be doing this part. Return tensors. Perfect. And the device I didn't hard also, it's CUDA. Perfect. So if we take a look at our tokens, it's basically words converted into integers, and the dictionary that it returns is the input IDs and the attention mask. But since it's a single prompt, the attention mask is just a series of ones, and this is not super important for us right now. So we have these tokens. Let's convert them into embeddings. So embeddings, and we can go click.encode and see what it gives us. So just send it to the perfect. So these are our embeddings, basically the tensor representation of our prompt. And if we want to take a look, we have a last hidden state as well as a Pooler output. And for the model, we're going to need the last hidden state, and we can just check its shape. And what we see here is the embeddings are in the dimension of 768. So now this seems to be ready. Now we will have to take our embeddings, the last hidden state, and send it to CUDA and cast it as torch.float16 so that it works with everything else. So, and call this our new embeddings. Perfect. So now our prompt has been embedded and is ready to be received by our model. Now, before we get into the actual loop to run our diffusion process, let's just take a quick look at the scheduler object. So this is a PNDMS scheduler. There's many different types available on Hugging Face, and the scheduler has many functions, but in our case there's one that we will be using, actually two that we will be using. First of all, the scheduler has, as the name suggests, the time steps. And we'll just take a quick look at the time steps. So what we see here are 50 time steps, and this is the schedule to denoise the image in question, which starts with the random noise. And the second thing the scheduler must do is provide us with the step function. So if we just take a look at here, this is a method within the scheduler that allows it to take predicted noise from the unit and denoise an image progressively. So now that we have all of this figured out, we can actually go into our diffusion loop and start running it. Actually, one last thing before we run the loop is let's just define a quick function that allows us to visualize the outputs. So this is a quick helper function that's going to help us visualize our images. And just to try it out, let's get some random noise. And let's make it 64 by 64. And let's try to see if we run it, if it works well or not. So tensor to display random noise, and what we see here is just a bunch of random noise. And what we'll try to do is run this through the unit multiple times as specified by the scheduler until a photo of a cat appears. Now let's get right into the main loop, which is the denoising loop. So for T, which is the time step, and here I'm gonna use TQDM just to be able to follow where we're at. And I have already imported torch for T in scheduler time step. And what we'll do here is, since we're not actually training but simply running the loop, we'll do torch.nograd to save ourselves some memory. Perfect. So first thing to know is that the random noise that the unit uses is it actually has 4 channels, not 3 channels, not red, green, and blue, but 4 channels that have no clear correlation to colors, but are just latent representations of for the unit. And what we'll do is, first of all, we're gonna scale the noise. So random noise is equal to scheduler dot scale model input random noise time t. Now we're going to run that random noise, scaled random noise, into our unit and go into predicted noise from the unit and run here the random noise, insert the time step and the embeddings as well. And this is gonna let the model predict what it thinks the noise is versus what the actual image is. And just keep in mind here that the random noise is on CUDA, but it's not casted as float 16, so we'll just cast it out, float 16. Perfect. And once that random noise has been generated, we'll ask for the scheduler for what it thinks the denoised image is. So we can say previous sample is equal to scheduler.step predicted noise, T for time step, and noise, and then finally what the random noise was initially. And finally the random noise the new random noise will be the previous sample, and this loop will run all over again until we have our final output. So let's run this out. Perfect. So our samples are out. Now we just got to scale them back by saying that previous sample. Let's check what type it is. It should be torch.float16. Perfect. So our latents are 1 over 0.18215 times the previous sample. Perfect. So now we have the latent representation of our image, and we're able to decode it with the variational autoencoder. So once again, with torch.nograd, simply to save a little bit of memory, we can say the output image is the VAE/.decode latents and take out the sample, and we can see what the output image.shape is. Perfect. So this is one image with 3 channels and 512 by 512 pixels. And if we compare it to the latents, we can see that it had one image, but 4 channels that are 64 by 64. So this is the correct image. This is not really an image. And we can now check it out and see what the image is with our function tensor to display. So tensor to display output image. Perfect. So we get something that looks maybe like a cat. Now obviously this was the simplest possible way to run Stable Diffusion. We did not perform classifier free guidance on this, and if we try to run it again, maybe we'll get something better. But by running it with classifier free guidance, you usually do get better image outputs. And there you have it. This is the simplest way to deconstruct Stable Diffusion 1.5 and to run it, to try to get something, to try to generate the images, to try to understand how the system works underneath. Hope it was helpful. Thank you.